Great. Welcome back, everyone. Hope that you enjoyed this interactive session, that you got to talk to your colleagues and fellow roboticists. It is my pleasure to now introduce our third speaker for this workshop, Cheng-Liu Liu, who is an assistant professor in the Robotics Institute at CMU, where she leads the Intelligent Control Lab. Prior to joining CMU, she was a postdoc in Stanford at the Stanford Intelligent Systems Laboratory. She holds a PhD from Berkeley, where she worked in the Mechanical Systems and Control Lab, and her primary research focus is designing and verifying intelligent systems that work with people, with applications mostly towards manufacturing and transportation. And she published the book Designing Robot Behavior in Human-Robot Interactions in 2019. It is our pleasure to have Cheng-Liu present today. Whenever you're ready, please go ahead, and we'll have some room for question, hopefully at the end. Thank you.
Cool. Thanks, Kim, for the introduction. So hello, everyone. I'm Cheng-Liu. It's my great pleasure to share with you some of our recent work on the safety critical learning and control for collaborative robots. So as Kim introduced, my work is primarily focused on designing those intelligent systems that can collaborate with human workers in production lines and also interact with other road participants on public transportation. So for example, these big collaborative robots or autonomous vehicles. There is one thing in common, that is they're all safety critical, and then because they interact with humans, which is highly unpredictable, so we need to deal with a lot of uncertainties while generating those safe control. And in today's talk, I will mainly discuss two of our recent work to ensure safety critical control. And the other work is based on the energy function based control idea, which is an idea that has been widely used in control theory to prove system stability or to prove system reachability. And the idea is also very intuitive. That is, if you want your system to achieve certain goal, then you will put the goal states at low energy values. And then you design your closed loop control system to be energy dissipating. Then eventually, if you let go your system, let it evolve automatically, then the system will eventually converge to the low energy state, which is the desired control objective. And then we can see an animation here. Yeah, so eventually you will go to the low energy state. And so in control theory, this type of functions, energy functions, called Lyapunov functions. And also in reinforcement learning, value functions also work similarly sometimes. And then how can we use this energy function-based idea to design safe control? That is also kind of straightforward. That is, we can assign low energies to the safe states and then high energies to the unsafe states. And then we design our closed loop control system to be energy dissipating. Then we can achieve the safe control. And in particular, we want to solve two major problems in safe control. And by the way, the safety specification considered in this talk will be a constraint on the state space. That is, we need the system state to be constrained on some subset of the whole state space. And this subset is called the safe set, which is denoted as XS here. And the two problems that we're trying to solve, the first is called forward invariance. That means if you start from this blue region, you should always stay in this blue region. And that means we should make the boundary of the safe set to be repulsive. So whenever you're touching the boundary, there will be some force to push you back. And then the second problem we want to solve is called finite time convergence. That is, if you start from outside the safe set, your system should pull you back to, or your control should pull you back to the safe set in finite amount of time. And both these objectives can be addressed using energy function-based approach. And before we dive into the mathematical details, let's first look at one example in human-robot collaboration. And I will discuss how we abstract out those safe sets and how we do the control here. So the left figure is showing the real-world situation with one industrial robot collaborating with one human. So for this kind of collaboration, we require that the robot should not collide with the human. And in order to compute this relative distance between human and robot, we abstract out the real situation into this computation model. In this computation model, we use capsules to wrap each link of the robot, as well as each link on the human body. And also the radius of those capsules are design parameters. So for example, we can assign large radius for vulnerable parts on human body, for example, head and trunks. And then with those capsules, we can greatly simplify the distance computation. And then with that distance computation, we can define our safe set. That is, the safe set contains the human state and the robot state that satisfy the following distance constraint. That is, any area occupied by the robot capsules should be at least gamma distance away from the area occupied by the human capsules. Yeah, and those capsules are denoted as the R and CH. And those capsules, location depends on the states of human and the states of the robot. States of the robot may be the joint position, and the states of the human may also be their joint position. So then we have a definition of the safe set, but since the dimensionality of the human and the robot is very high, it's very difficult to visualize the safe set. And here we provide a very simple illustration in 2D where the horizontal axis represents the robot state, the vertical axis represents the human state. And if suppose at current time step, our system lies in this point, as human state is here and the robot state is here, then that means we are safe because we are in a blue safe region. But if we anticipate that the human will take a move, go into the unsafe area, then the robot should take a motion to pull the system back. And to automate this process, we can introduce this energy function-based idea. That is to define an energy function on top of the system state space, such that the sublevel set of this energy function is the safe set, as shown in the figure here. And then because any control input that combines the human control and the robot control, any control input to change the system state will result in a vector flow on the surface of this energy function. So then we can use we can judge whether this control is safe or not using the fact how this control is changing the value of the energy function. So for example, if the control is driving the energy function above the level set, then it's an unsafe control. And if the control is driving the energy function back into the safe set, then it's a safe control. And then we can use this to either verify whether a control is safe and also to use this to design a safe control law. And here, because we're focused on safety, so then we call this energy function for safety as the safety index. And then we can use this safety index to derive the safe control. Suppose our system dynamics can be written as this ODE, which is affine in control. That means the control term does not enter the nonlinearity. And we have this x dot equal to fx plus gxu. And then we can compute how the control will change the safety index, which is phi dot equals to LF phi plus LG phi multiplying U, where LG phi is the lead derivative. And here one more thing to mention is that if we're considering the human robot system, then this ODE should contain both human dynamics and the robot dynamics. But this control U is only the robot control input. And as we said earlier, we have, in order to make sure our control is safe, we need to add some constraints on phi dot on how it will evolve throughout time. And then this constraint on phi dot can be translated into constraint on our control U using this relationship. And also that depends on the system dynamics. So for example, if we want phi dot to be smaller than some negative eta, and this eta can be a function that depends on phi, And then our control U needs to satisfy this half space constraint. And we call this half space constraint as the set of safe control. And if we illustrate this constraint in a control space, it is something like this shaded area. And why it is a half space constraint, that is mainly because we assume the system dynamics is affine in control. If it's not affine in control, then we won't have this good property. And since we have this good property, then we can use this half space constraint to modify any nominal controller, which may generate unsafe control input. And this modification can be easily done by adding the safety constraint as a supervisory loop to any nominal controller. This nominal controller can be any like PID controller, LQR controller, MPC controller, or any reinforcement learning controller, which generates a reference control input UR. Then our safety controller will monitor the output of the reference controller, of this reference control. And then always, if it does not belong to the set of safe control, you'll always try to project it back to the set of safe control. And then using this kind of strategy, we can guarantee that the system will always stay safe. And we have applied this kind of method in a wide variety of systems. And here I'm showing one application on industrial robots. And in this video here, we're using safe control to wrap a long-term planner in order for the robot to safely interact with this pink obstacle while still finishing its task by placing this black workpiece into this green box. So the safety controller is actively monitoring the reference trajectory, this yellow trajectory generated by a long-term planner, which updates at around 1 Hertz. And while the long-term planner is generating new plan, the safety controller will try to modify this robot trajectory if it detects that the obstacle changes location and which makes the original long-term plan no longer safe. Yeah, as we can see, this is very effective in guarantee real-time safety. And this safety controller in this case runs at 1000 Hertz because it's basically just solving a quadratic programming, which projects the nominal control from the long-term plan to the set of safe control. So far, everything is good and works perfectly. But that actually depends on a very, very strong assumption. That is, we have a very good system model. But in a lot of cases, we don't have a good system model, especially if the robot is trying to learn its own dynamics and try to learn how to control during the interaction by interacting with the world. Then how can we deal with this case? How can we deal with those either no model or we only have a black box model? So here, to simplify the problem a little bit, we assume that we have a neural network dynamic model, which can be learned offline. And this neural network dynamic model may no longer be control affine. So the approaches we discussed earlier does not apply. And how can we design new computational methods to guarantee safe control for these kind of models is one challenge I will talk about today. And the other thing is, during the human-robot interaction, the robot needs to properly predict the human behavior. And the human model is also something the robot needs to learn. But due to the diversity of human behaviors, how can we ensure that our learned human models are general enough to different individuals and different tasks? That is also one thing we need to address. Okay, so we'll start with the first question. How can we do safe control if we only have a black box model? As shown here, which is assumed to be x dot equal to fxu. And as a result, we can see that phi dot is also no longer a linear function on u. Now it depends non-linearly on u through this relationship. And in order to still derive safe control in this black box case, we need to revisit a little bit on the energy function based safe control. So in our previous discussion, we simplified several parts. ideally, if we want to synthesize safe control for any dynamic system, we need to do 2 steps. First step is to find safety index, the energy function, such that we can always have a safe control, have a feasible safe control, even if we have constraints on our control space. And then the second step is to compute the safe control in real time. So our previously discussed QP formulation, quadratic programming formulation, addresses the second question. But now we also need to consider the first question. And also, since we don't have a control affine system, the solution for the second question also need to be modified. Okay, now before we discuss the solution, let's take a deeper look on the kind of the ideas of this safe control. So we are illustrating this energy function here, which is on top of the state space. The horizontal plane is assumed to be the state space, where the safe set is marked as blue, and the energy function is shown as this surface, whose sublevel set is the safe set. So we need to make sure that for all the states that is above the level set, its future control is driving the system back towards the safe set. So the blue area means the feasible control flow in X dot. So we need to make sure for this X1, this X dot should in this blue area so that it will flow back, and X2, similar idea. In X3, it's on the boundary of the safe set. So we only need to make sure that the X dot, the future evolution of the system won't go out of the safe set, won't go above the level set. And then these kind of constraints on X dot can be translated back to the constraint in control U through the dynamic function X dot equal to FXU. And because now we have a very complicated black box dynamics, so the shape of the corresponding safe control set will look very differently, no longer a half space. And then what we need to make sure is the projected back safe control, this blue area, should always have a non-trivial intersection with our control limit, as shown in this orange area. Because if the safe control exceeds the control limit, then that means if we arrive at that state, we have no choice to stay safe. Yeah, so the goal for synthesizing the safety index is to make sure that for every state, we should be able to find a feasible safe control. And once we have that safety index, then what we can do is just use that safety index to monitor the monitor the nominal controller in real time. So for example, the nominal controller would generate some nominal control, and then we check if it belongs to the safe control or not. If it belongs, then we execute it. If it does not belong to the safe control, then we project it back to the safe control. Okay, although the projection is also non-trivial in this case, as the safe control set is no longer a half space. So how can we efficiently do this projection? Let's look at an example for neural networks. So in this neural networks case, the projection problem is shown as this optimization, where we also try to minimize the difference between your final control and the reference control constraint on the this phi dot smaller than negative eta constraint. So if we look at this problem, it's actually very similar to input adversarial bound problem that neural verification people solved a lot, because the objective is an L2 norm in the input space, and the constraint is only a constraint on our output space. So for example, this kind of problem can also, this kind of mathematical form can also encode adversarial attack problems to image classification networks. In those problems, people want to find the smallest perturbation to an existing image, suppose it's UR, such that the label of the image will change. And that can be encoded as an output constraint. And also that output constraint should go through the neural network. And with this understanding, then how about we just borrow the tools in neural verification domain to solve our problem in safe control? And before that, let's do a quick review of what are the tools in neural verification domain to solve this kind of adversarial bound problem. So there are basically 3 types of methods to solve general neuralification problems: reachability-based method, optimization-based method, and search-based method. So they all kind of solve the input-output satisfiability problem. That is, given some input, whether the output of my neural network all belong to some output set. And if we trickle this formulation a bit, it can be used to solve the input adversarial bound. So then how does reachability type of analysis solve this kind of input-output verification problem? That is, instead of checking the output point-wise, we try to propagate the whole input set, which contains infinitely or uncountably many points, as a whole through the neural network. So there's no longer point-wise validation. What we are doing is directly propagating a geometric objects layer by layer through this network. And after this kind of propagation, we find a reachable set, output reachable set on the last layer, and then we can check whether this output reachable set belongs to our output constraint or not, and use that to verify our specification. And then the second type of method is using optimization, which directly writes everything, encode everything into optimization. This optimization is actually similar to the one we saw on the previous slide, but it's taking a more general form. So for example, if we want to check if for any X belong to this input set X, Y belong to output set Y or not, we can try to falsify the claim by encoding the negative of the specification into the constraint. And then if we can solve one input that satisfies this negative claim, then we find a counterexample. If we cannot find a solution, then that means the original specification holds. The major difficulty in solving this kind of optimization is that we have a very complicated equality constraint on the neural network. And then in order to make sure we can handle this complicated neural network constraints, people introduce a wide variety of relaxation methods to encode especially the nonlinear activations. So for example, we can encode the nonlinear ReLU activation as a triangle area. There's some relaxation, but after we relax it into the triangle area, the whole optimization problem becomes a convex optimization, which can then be easily solved. And the third type of approach is using search. And search-based method is usually combined with either reachability or optimization, because there may be some over-approximation in either approach. And then search-based methods try to partition the input space into smaller regions, because usually if we verify smaller regions, then the over-approximation will be smaller. So then it's easier to be complete with smaller input region. And then if even with the smaller input region, our method is still not complete, we can keep splitting and until we find some satisfying solution. Okay, so that's an overview, and all these methods have been implemented in our toolbox called neuralification.jl. So that's an overview, and how can we use those neuralification approaches in solving the safe control problem? Here we choose to use optimization-based approach to solve our safe control problem here. And the idea is we can use a special encoding to make sure that this constraint with respect to neural networks can be, this is actually a nonlinear constraint, can be turned into some linear constraint. Okay, and here we illustrate how we do it. Suppose we have a feed-forward neural network with ReLU activation. Then the ReLU node can be written as the following constraints. Z hat is the pre-activate value, which depends linearly on the nodes on the I-1 layers. And then we have an activation function delta, which is 1 if Z hat is greater than 0, if it is 0 if the Z hat is smaller than 0. Then the final output of the node Zij equals to the delta multiplying Z hat. So this is highly nonlinear, but we can use mixed integer linear encoding to turn this nonlinear function, value function, into this mixed integer encoding with 4 linear functions. And so for the sake of time, I'm not going to go into the details, but if you're interested, you may check our paper on this. And after we do this encoding and then add the original minimization back, the overall problem then is changed into a mixed integer quadratic programming, which can be solved much more efficiently than directly solving the original nonlinear programming problem. And with that approach, we can then perfectly solve the second question that we raised earlier. And then the only thing left is the first question. So although we have a good approach to compute safe control in real time with respect to a black box model, but then how can we guarantee that we can always find that safe control, especially within the control limits? That requires the synthesis of the safety index. And the goal of the safety index is to make sure that we always have this condition. The safe control intersecting with control limit is not an empty set for all x. And in order to achieve that, we can actually formulate the following minimax problem. That is, we try to find the possible safety index phi that will maximize the minimum area of the feasible safe control. And this minimax problem is also can be solved very efficiently if we properly parameterize the safety index phi and then optimize, like solving this optimization using an evolutionary method. For details, I think my student Tian Hao just presented this paper in the poster session. And here I'm going to use his example to explain a little bit more about this, how everything is done. So he used a second order vehicle model encoded in neural network to perform this testing. And in this example, we require the vehicle to avoid this obstacle. So the safety requirement is that the distance between the vehicle and the obstacle should always be greater than or equal to a minimum distance threshold. And then we can parameterize the safety index as the following form. The reason why we can parameterize it that way is because it is proved in our previous paper that as long as we can find a non-empty feasible safe control, then the set phi 0 smaller than 0 and the phi smaller than 0, this set is always forward invariant. That means if we start from this set, we will never leave this set. And the reason why we cannot directly use the original phi 0 is because on the boundary of this phi 0, there are some points that is inevitably will fail. So for example, if we are on the boundary of this phi 0, that is distance between the vehicle and the obstacle is exactly d min, while the vehicle have some relative velocity towards the obstacle. And since the vehicle is second order controlled, then we cannot immediately stop this vehicle. So then the failure is inevitable. Then what we need to do is to avoid getting into that part of the state space in the first place. And by defining this phi, it can help us to exclude those kind of states that currently is safe, but will lead to inevitable failures. Okay, and let's see how this then the learning approach can help us optimize the parameters in this newly designed phi. So to illustrate the learning, we introduced this phase graph where the horizontal axis is phi 0 and the vertical axis is the derivative of phi 0. So originally, our safe constraint is the half space to the left half space. But as I said earlier, this original phi 0 is not a qualified safety index because for x2 here, it does not exist any safe control because in this x2, its distance is on the boundary and there's a huge relative velocity from the vehicle towards the obstacle. Then after some optimization, we exclude this X2 from our safe region. And we get a boundary like this. And in this case, all the states now have safe control. And if we optimize it further, we'll have like a larger area for the feasible safe control. And if we use that, learn the safety index, and then do the real-time safe control using the mixed integer encoding, then we can get those safe trajectories. And this approach demonstrates that even with black box models, we can successfully do the safe control using energy function-based idea. Although there's a limitation, that is the computation speed is also a constraining point if the neural network is very big. So then we still need to speed up the computation efficiency for those neural verification methods. Okay, so that's the first challenge and how we address it. Then the second challenge is how can we efficiently learn human models so that they can generalize to different individuals and different tasks. So the reason why we need a good human model is because those human model will generate uncertainties, and we need to incorporate those uncertainties in the safe control. If there's larger uncertainties, then our safe region will be smaller and the robot needs to generate larger detour. And our hope is that we can learn good models such that the uncertainty range is small. So then we can do like a safe control non-conservatively. And how do we do the human model learning and human prediction? The idea is we first get, oh, I see a question. So should I address the question?
We can address the questions at the end. Yeah, you can keep going.
Okay, great. Cool. So the human prediction pipeline will first collect a bunch of human data and then throw the data into some machine learning methods, then it will produce our prediction model. Then in the real time, we take the real time human motion and then use the prediction model to predict the future motion. So the biggest challenge in this pipeline is that there might be distribution shift between the offline collected data and the online measurement. And how can we deal with the distribution shift is the key challenge. And this distribution shift may be that we collect data for people A and then test it on people B, or the people A is doing task A, but then in the real time, the people A now doing task B. These all will create like a significant distribution shift. Then in order to deal with this kind of distribution shift, we introduce two methods. First is to do online adaptation. The second is to do the data augmentation offline. So online adaptation is very helpful in our research to help minimize the prediction error and also minimize the uncertainty. That is mainly because we observe large deviations among individual humans, so that a lot of times the model learned on one human subject needs a lot of adaptation to be applied to another human subject. And also even within the same human subject, they may exhibit time varying behaviors, which also need adaptation. And one example is shown here. So if we look at the elbow location, we can see without adaptation, there will be huge prediction error. And after adaptation, the prediction error is reduced. That is mainly because in our data, some people is lifting their elbows while doing the assembly, and some people is resting their elbow on the table. But in this testing case, the human is resting the elbow on the table. And after adding this adaptation, the model understood that, okay, this human is doing this kind of motion. So then the prediction error significantly drops. And then what are the methods for online adaptation? So that's basically, we can use all the methods that we do the offline training for online adaptation, which is just to bring the computation online. And so for offline training, we can either use first order method or second order method, although for offline, first order methods used more frequently. For online adaptation, what we find is that second order methods generally perform better than the first order methods, which actually align with our intuition that usually second order methods will converge faster if we are already very close to the local optima. And because our network is properly trained offline, so that means the initial value is already close to the local optima. So then in adaptation, while we are using second order method, it performs better than the first order methods. Oops. Oh, and one more thing, that is to implement second order methods online, it's important to add forgetting and smoothing as low pass filterings to filter out the noisy hashes. Otherwise, the learning can be unstable. So here are the results for our second order based adaptation on the task that we saw earlier. And we demonstrate the performance for adapting to different humans and the performance for adapting to different tasks. So our method is the red one. It outperforms all these state-of-the-art methods, which is good. And also one interesting pattern is that for adapting to different humans, the errors are in general larger than the errors while we adapt to different tasks. So then this confirms that the individual differences is more significant than the task differences. Okay, cool. So that's how we perform online adaptation to address this kind of distribution shift. But one drawback of online adaptation is that we cannot control the data flow that gets into our adaptation system. So that means it may, if our learning rate is not properly designed, our filtering algorithm is not properly designed, that may still lead to safety hazards. So how can we do something offline to mitigate this distribution shift? And actually, yes, we can do some data augmentation before we deploy the model in order to compensate the distribution shift early. And here we use a different example, but still this human prediction task, but different. But now we do intention prediction instead of trajectory prediction to illustrate how we can do the offline data augmentation. So in this intention prediction task, we want to predict what the human wants to pick and whether the human wants to assemble the two work pieces together or do something else. So in this case, why do we need to augment the data? The reason why is that the label in our like naturally collected video sequences are highly imbalanced. So in our case, there are much more assembly data than those reaching and the retrieving data. So as a result, the assembly prediction accuracy is much higher than the prediction accuracy for others. And also when we want to deploy this kind of prediction model to the real world, there will be a lot of disturbances. So maybe the ground truth of the human motion is following the red line, red dots, but the perceived trajectory is the purple dots. And then how can we make our model robust enough to defend itself against those disturbances? It's a huge question. And both of these factors will lead to poorly learned decision boundaries. And we want to augment our data to help us properly find the correct decision boundary. Then how can we do that? How can we help out our model to find the correct decision boundary? Our idea is to add those data that is most confusing to our current model, and then ask experts to label those data so that we can learn more. And what are the most confusing like area of the current model? In our case, we believe it's the data on the current decision boundary. So here's an example. Suppose we have this 2D classification problem where the ground truth is shown here. And we have the data point, and with those data points, we can learn a model. Then the most confusing parts are the boundary points on the current model, because a slight perturbation will change the output. We want to make sure exactly that this learned decision boundary is the correct decision boundary. And once we can find those confusing points, we can ask experts to label its label those points and then add those points back to our data sets and so that it can help us detect the correct decision boundary. And here is an animation to show this process. So the left is showing the learned model, the right is showing the augmented data. At the beginning, we initiate from a random initialization and learn first round using our offline collected data. And then with the learned model, we try to find the decision boundary and find their label as shown here and add those data back to the training. Then after train on the newly added data, the decision boundary changes. And then we find more confusing points. And by iterating this process, we can see a convergence trend towards the ground truth. Okay, so this idea is very nice, but practically, how can we find the decision boundaries for deep neural networks? It's still a very challenging question. And this is equivalent to do the following testing. That is, for any current data point we have, does its neighborhood have any point that generates a different label? And if it does, what are those data points and can we find it very efficiently? So in the real application, so for example here, what we do is we try to perturb the human trajectory within certain range and see if that perturbed human trajectory will generate a different intention label. And back to the simple 2D problem, what we do is for every data point, draw a ball and check if the color changes inside the ball. If it changes, then we add the closest point that the color changes. And then we can do this efficiently using the neural verification methods that we introduced earlier. So then with that completes the whole data augmentation pipeline. So there's a lot of things going on. Let me explain it piece by piece. So we initially have the training data. And then with the training data, we can do the network learning. And with the learned network, we can do the formal verification, which is to try to find the boundary points of the current model, which is most confusing to us. And then once we find those inputs, we'll see if we need to ask for human labeling, because some inputs we can directly view them as adversarial attacks, which does not carry any meaningful semantics. But for something, if the scheduler cannot decide, then we'll ask for human verification. If human verify that data, we'll add those directly to the training data. If human cannot verify, or we believe it does not worth humans' effort, then we'll directly throw it back to the adversarial data. The adversarial data will only be used in the current epoch in the training. In the next epoch, it will be forgot. And the training data will be carried on and on. So then with this loop, we can show that our training process can keep improving the accuracy, while other methods will overfit at some point. So the overfitting for supervised learning is okay, but for the conventional adversarial training is significant. That is mainly because it does not have the expert guidance, and it's possible that it added a lot of adversarial data which has wrong label. Okay, so that's how we answer the second question. So we answer it through online adaptation and efficient data augmentation through verification. But there's still some limitation, that is how we can minimize human efforts in this labeling procedure. That's also something we're working on. And I want to conclude with some of our work on the human-robot collaboration, especially for the desktop assembly. This is an NSF-supported project, which we enable the robot to help human in assembly, where the robot will infer human intention, then help deliver a tool to the human to finish that. And currently, we are trying to expand the robot skill set to let it work on more sophisticated tasks. So for example, instead of just handing over, it can perform some cable assembly, perform some insertion. And we believe that will greatly improve the helpfulness of those human-robot interaction and collaboration. With that, I would like to conclude my talk, and the work presented here are all done by my students Tianhao and Ruixuan, and here are some links if you are interested. Cool, thank you, and I'm happy to take questions.
Thank you so much, Cheng Liu, for this very thorough talk. We have time for some questions, so if you'd like to unmute yourself and ask a question, or you can raise your hand, go ahead.
Shall I address the first question in the chat?
Yeah, maybe Shreyas, you can ask your question.
Yeah, thank you so much for the great talk. So can you give us a feel for how complex the neural network model can be for your verification safe control method, and how you might incorporate model uncertainty? So if the neural network is not perfect at modeling the robot.
Yeah, so for now in our test, the neural network is actually a pretty small network. It is a feed-forward network with only 2 hidden layers, and I believe each hidden layer is about 40 or 50 neurons. So altogether, it's just a couple hundred neurons. It still requires a lot of work to scale it up to the real world level neural networks. And how can we incorporate uncertainty? That's a great question. That's also something we want to explore. So one idea is to use model ensembles, that is multiple neural networks, and then we try to defend the control system, or to derive a safe control that is safe with respect to all the models. Another idea is to use Bayesian neural network, which associates a distribution with the neural network parameters, and then we can make sure that our safe control is robust to all the distribution. Cool.
Great. Any other questions? So as I said, you can either raise your hand or just unmute yourself. Sorry, now you can unmute yourself. It was not allowed earlier. Okay, well, if there's no other questions, maybe I will ask one. Can you talk a little bit about, so you mentioned your last project on human-robot collaboration. Can you give us a sense of how the more theoretical approaches that you've taken can have a concrete impact on a collaborative task, for example, like the one that you showed?
You mean how the theory can affect the implementation?
Yeah, so let's say that you're running a controller, let's say a basic controller or a basic way of somehow controlling the behavior of the robot versus one of your approaches. What kind of a concrete difference would that make in terms of the actual interaction, let's say, with a human?
Can you give an example, like what kind of method are we compare against?
I don't really have a sense of again, so I'm not in the field, but I'm thinking more in terms of like, okay, from the human's perspective, interacting with this robot. Let's say that some of your control methods were used, for example, for more advanced or more intricate types of tasks. In terms of the performance of the robot and in terms of maybe how robust the collaboration would be, do you think that there is something that is to be gained somehow from the application point of view?
I think there's one thing our method has not addressed is how to make the collaboration favorable to the human. So our work is mostly on like suppose human is doing something, and how can we make the robots coordinate with human without thinking about the human factors? But that's definitely a huge limitation in our work, and we need to bring some more advanced theory that model human behaviors into our framework. And I believe there can be a lot of opportunity to combine those modeling with our safe control and also robust prediction. Our robust prediction is more on the short-term prediction. so that it can be used in safe control. But the psychological factors may create long-term effects. And if we can also model them, then it can make the collaboration like favorable in the long term.
Yeah, there's definitely lots of research challenges there for sure, whenever you put a human in the loop. Thank you so much, Cheng Liu, for the talk. Once again, round of applause. And I think we're ready to move to our last speaker. So I'll give the floor to Philippe to introduce the next speaker.